So I'll be talking about methods for analyzing target attacks with Office documents. Uh, okay, so we'll start off with an introduction to target attacks, what they are and how they work, and how people use them. And then I'll talk about the Office binary file format, which we released to the public like a couple months ago. Then I'll talk about the type of bugs that we have in Office that people exploit. Then we'll talk about the defensive mechanisms, what you can use to not get owned. And then I'll talk about the exploit structures, like how the exploits work. And then we'll talk about how to analyze the exploits. And finally, we'll talk about AV/IDS detection for these things. All right, I'm gonna go through this pretty fast because it's lunchtime, like after this, so I'm sure we're all looking forward to it. And I'm very tired. Yeah. So target attacks, so these are pretty much, you have an adversary, they have a target. Typically, the target has some type of resources that they need access to, and usually the target is fairly well protected the network perimeter. So what they do is they'll attempt some client-side exploits. So what they do is they build some Office document, Adobe PDF, whatever. They'll send it in to this individual that they're targeting. So they know ahead of time who is going to be the victim. And most of the time, they know they know what this person does, what kind of work he does, and even the people that report to him. So I mean, it's a lot of reconnaissance work that they've done. And most of them, they'll spoof the email so it looks like it's coming from your coworker. And it's very effective. Bypasses like probably most of the perimeter security devices, so firewall, IDS, IPS, most of them don't detect this stuff, and so it goes through. And most AV engines can't detect it either. And there's no public information on this topic for some weird reason. The media talks about it, but they never go into details, so I'll tell you today. All right, so Office file format. So all the Office file formats starting from Office 2003 below follows this structured storage format. And this is not only used in Office, this is used in a whole bunch of other files, like MSIs are actually LASS files. And it's literally a file system within a binary file. And you have two units. You have storages and streams, and storage is like a directory, and stream is like a file. And the spec for this is pretty small, it's like 12 page. And then each of these applications, for example, PowerPoint or Excel, they'll store their data inside specific streams. And each stream has a name. And it can be very frustrating to parse manually, so don't do it unless you have to. Yeah, it's very frustrating. Instead, use we have COM APIs that will do this for you. Here are some of the functions that you'll need. So all you do is you call SDG open storage on the file, and you tell what kind of permissions you want, read, write, access, blah, 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 blah. And then you get back an iStorage object, and then you enumerate through all the elements, which basically enumerates through the storages and streams. And then you pick, when you find a stream that you want, you just call OpenStream on it, and it'll return an iStream object, and then you call stat on it, and you get the stream length. And you can do read, and then after that you can do read, write, to that stream, whatever. So it's very similar to open, fstat, read, blah, blah, blah. Here is some code example of how to do that. This is somewhat compilable. I think I stripped out some stuff to make this fit, but this will work. Or you can do it if you don't know C or C++, or you don't want to work with Win32 API, just use Python. If you use the Win32 COM wrapper from Python, it does the same thing. All it does is just wraps our Win32 API. And it's actually very easy to use, as you can see here. And then you get all the facilities that Python gives you. It's very good for experiments. If you want to write a fuzzer or something like that, it's pretty easy. All right, so I'll give you an example here for PowerPoint. So PowerPoint stores all this data, for example, like the slide content in the stream called PowerPoint document stream. So if you call enum elements on this, you'll see a stream called PowerPoint document, and it's in Unicode, so you'll see like P and then 0, O, 0, blah, blah, blah. And then PowerPoint internally has the data structure has two data structures. One is a container, which is also it's analogous to a directory, and it contains, and then an atom is a file, and a container can contain files, or a container can contain other containers, and so on. And then the records follow the TLV format, TLV style. MSO objects follow the same format. MSO objects are like these charts, not charts, but these GUI components you can put into Office. And this is what MSO.dll, think of that. And then there's a structure to define the PowerPoint, which is, there I give you the information there. And based the way you recognize if a record is a container or an atom is based on the rec_ver. If it's OXF, then it's a container, else it's an atom. And the rec type refers to the record type, and the record type is what we release to the public. Like if the record type 1000, what is that? And you go up, you download the file spec, you say, okay, scroll down, type 1000, what is it? And then we'll give you what exactly the data structure for that record is. And there are about 100 of these. Excel has quite a few, and MS Word has quite a few as well. But PowerPoint is very simple, only 100 or so. And I drew this, so it's easier to understand. Here's another one. Can you guys see it pretty well? Yeah, this is an abstract view of when you open up the stream and you read the buffer, that's what it'll look like, and that's how you parse it. You'll have to do it recursively because the containers can contain other containers, but given that, it should be pretty simple. Here is so if you were to parse this is what it will look like. This is a real this is a real PowerPoint document, and the first record that you'll see when you read it from it, it's going to be a document container, which is type OX3E8. And then that container will contain an atom of type OX3E9, I showed here, and so on and so on. And if you notice at the bottom, there's like a slide container. So all the content for a slide, for example, the bullets, the text, that is stored for each slide. There's going to be a slide container. So if you had like 100 slides, there'll be 100 containers, 100 slide containers. For Excel, the data is stored inside the workbook stream, and it doesn't have containers or atoms. It just has follows this BIF record, which is very similar to it's still TLV, and BIF records can have can only be up like 8,000 bytes or so. If it's bigger than that, then you need to use another a BIF record type continue that says, hey, there's going to be more data coming up, and then you follow it. So it's pretty simple. Bugs. The bugs in Office are, just like any other apps, it's nothing really out of the ordinary. You still have, standard stack, heap overflow, uninitialized variables, bat pointer reuse, double freeze. A whole bunch of these. This is very common. Nothing special. Here is, I'm going to do a demo. This is a pretty innocent sample. Innocent demo, but in real life, what happens is the attacker will perform reconnaissance on the target first, so they know, like for example, if they know that some of you are if they were to attack me, they would know that, oh, I'm going to recon today, and I would probably want to look at the recon schedule. So what they'll do is they'll craft up the recon schedule in a Word document. They'll send it to me, and it says from Hugo. It says, hey Bruce, check out the updated recon schedule. And I would open up, blindly, and then I get owned. Sorry, my virtual PC is a little bit slow, so. There you go. So if you notice, there was a little bit of lag there. Like I actually started, and then it exited, and then I relaunched it again. So, anyways, that's what it'll look like on a faster computer. This stuff will be very fast. You won't even see the application quitting. It will be like just like opening a normal document. All right, the defensive mechanisms, there are a few. You can use malicious. It's a free tool that we wrote in response to these things. It requires Office 2003, and basically what it does is it only works on LASS files. And what it does is it converts your binary file format into the new Office 2000 file format, and then opens it up. So you won't see, even if there were vulns, it won't be there. It'll just crash. Or you can use, if you have Office 2003, just go install Office 2003 SP3, which we released, I think, in September or December. I can't remember which one. And it's also free, and this is a major security push. We fixed a whole bunch of bugs here. And the fact is, if you had Office 2003 SP3, then none of the 0 days that were released or patched, since it's released, you won't be vulnerable to any of them, because none of them affect 2K3 SP3. In fact, there are very few bugs that affect 2K3 SP3 so far. So for your own safety, if you can, go install SP3. And together, SP3 and malicious actually eliminates probably, I want to say 100%, but you never say never, right? So about 99% of them. In fact, I don't think I've ever seen one that doesn't work, but I always want to make sure. And always have the latest patches. Or you can use Office 2007. It's pretty cheap, actually. If you buy the home edition, it's like $60 or something like that. All right, the exploit structure. It's nothing special. The basic structure is going to have shellcode, and you have some malware that's embedded sometimes. Or then you have a clean document which opens up, and then I'll talk about the techniques. All right, here's another picture that I drew. So the picture is actually the complete Office document, and I guess structured view of an Office document. You have an LASS header, and then some Office records, and then you have some shellcode, and then you have some more Office records, and then you have a Trojan or malware. Sometimes you have one. Sometimes you have more than two, and then you have a clean document, which is what they use to reopen, and then you have somewhere which is like the LASS stuff, and there can be variations of this. But the green parts, they don't change often. Because, for example, if it's not an LASS file, obviously Office is not going to open it. Or if you have too many corrupted Office data structures, Office sometimes will pick this out and then say, oh, your file is corrupted, and not open it. And most of the time, you'll see that the clean document and the Trojan is going to be obfuscated. So you can't just look up in a hex header and say, oh, yeah, that's a P header right there, and oh, that's going to be my Trojan. It's not that easy. And they rarely use URLmon. For example, everything is inside one document. They don't ever call back home to download a new set of Trojan. It's always, the Trojan is delivered along with the document. This is very different from the other client-side exploits. For example, the stuff that can be done through JavaScript. Most of the stuff, if you look at it, like the ActiveX stuff, in the shellcode, what they'll do is they'll just call it URL download, like download file A or something like that, and then that to pick up the Trojan and call winexec on it. They rarely do it for Office documents. The techniques, it's standard get EIP, and then sometimes they have custom encoders. In fact, about 99% of the time. And then some of the other techniques, you use file handler brute force and application relaunch, and we'll talk about them in a bit. All right, so why do they brute force a file handle? So basically, when you load up, when the shellcode runs, what it'll do is it'll brute force all the file handles, then it will compare, it'll call get file size on each of the file handles, and then compare that with a known size. And if it matches, it says, ah, yeah, I found myself. And then when it matches, and then it seeks to certain offsets to extract the Trojan or the clean document. So, and why do they do this? I mean, there are a whole bunch of other ways to find yourself in memory, right? You can imagine there are a lot of ways. But this is the easiest method, and it's the most effective, and it's the shortest method. You can do this in assembly in probably like 9, 10 instructions. All right, so here's what it does, yeah. Shellcode runs, decodes itself, builds up a list of function pointers it needs, create file, set file pointer, write file, winexec, create thread. Yeah. Sometimes get temp path, get temp path or something like that to get your temp directory. So that's what it'll do. It'll extract the Trojan and then write it to the temp directory. Pardon? I'm not, oh yeah, oh, someone should have told me this. There we go. Thank God I didn't have like notes on there. Anyways, yeah, so basically, so after it finds, the shellcode decodes itself, builds up this list of function pointers that it needs, and then it finds itself in memory, basically go through the file handler brute forcing method, and then it seeks, calls set file pointer to seek to a specific position that it knows that that's the beginning of its Trojan, and it reads that buffer and then writes it to disk, and then call winexec on it. And then it reads the clean document using the same method, and then it writes it to disk, and then literally call Office again to open that file, which is why you see when I open it up, it quits and then it reopens again. That's the result of that. So pretty interesting. You can apply this method to any other exploits that are in binary file, like PDF or even like MPEG files. It's a very effective method. Okay, the analysis techniques. The tools you need, just need a hex editor, disassembler, and optional if you have a debugger. WinDBG is good. The objective is, one, you to identify the shellcode, understand it, extract the malicious components, and if you have the time, to identify the exact vulnerability that they're trying to exploit. Okay, so I don't have any assembly, I just have opcodes. So earlier, yeah, this morning, yeah, my friend Pete here, he recognized, I think, all of these except for two. I don't know if any of you recognize this stuff. Anyone? Besides, like, the obvious ones. This is REcon. I mean, this is what people read for a living, right? Anyway, so fine, I'll just say it. The EB is going to be a short jump. The E8 is calling backwards. E2FA, that's a loop. And then you'll see 33C9, that's XOR ECX, ECX. So you can see that they're calling in this is standard get EIP technique. 64A1300, that's, anybody know what the 64 prefix is for? No one knows. Yes, yeah. It's for the, so any instruction involving a DFS segment is going to have the 64 prefix. And 64A1 is to move FS30 into the EAX register. If it's EBX or ECX, it's going to be like 8B1D or 1E or something like that. And what are the last one? D97424F4? No one knows, okay. You guys are not very excited. Probably because lunchtime is soon, so. Okay, so D97424 is a floating point instruction, FNSTNV. It writes the current FPU control environment to memory location, and just one of the data block that's written, it just happens to be EIP. That's all. All right, so the other one is, so how are you gonna debug this stuff? Right? You obviously can't open up a doc or XLS file in a debugger. So what you have to do is be a bit more creative. So, method one. You identify the shellcode, you open up your hex editor. Oh yeah, I forgot to go back here. If you don't know any like opcode at all, but if you load a file up in IDA in binary mode, sometimes, but not all the time, sometimes IDA will actually pick up the shellcode because it has like, apparently IDA has some heuristics to pick out like push EBP, move ESP EBP and stuff like that. So it actually picks up some of that stuff. But sometimes it doesn't work. Maybe OFAC can add those more heuristics or something like that. That's a feature request, by the way, OFAC. All right, so method one is you open up in the hex editor, you find the block that it has you suspect to be shellcode, and you patch the first few bytes with OXCC, and then you start up Office and attach WinDBG to it. If you did it right, then you'll hit in a breakpoint. If you did it wrong, then you probably got owned because the shellcode ran and you didn't know it. Yeah, so I mean the way I usually do it is to make sure is I open up the file in IDA first, and then actually go to the parts that I suspect to be opcodes. I press C, and if it disassembles and it looks likely, then I patch it, and then let's see what happens. Yeah, sometimes I fail though. So method two. Pick any executable, and you copy the shellcode to it, and then set EIP there in single step, just like any other executable. This is actually a pretty common method. Most AV analysts use this. All right, method 3 is to use WinDBG. What you do is you save the entire Word document in a temporary file, like a bin file, whatever. You open up Notepad or any other exe, attach WinDBG to it, and then you call dvlock. Anybody use WinDBG here? Ooh, lots of people. Anybody knows what dvlock does? Besides Nathan, yeah. So what dvlock does is allocate a block of memory with read, write, and execute permission. And then read mem is kind of obvious. It reads the content of a file into a block of memory. So what you do is you figure out how large this file is. You allocate a block of memory to store that, and you read the file into that block, and then you figure out what the shellcode is, and you set the EIP to that, and then you can single step. So it's very effective. You can actually, so you don't need Office at all. And this is, yeah, if you have WinDBG, this is probably the best way. So here's an example. That's what I did. You probably won't be able to see all of it, but yeah. All right, the method 4 is this is the best one. You do the same thing, except for don't open like Notepad, don't open like calc.exe, but open Vim or Notepad or anything that opens a file. And the reason why we do this is because when the shellcode runs, it'll do a brute force on the file handle, and you'll get a match, right? Because you use like Notepad or whatever, and you open this file. So you have a file, the process will have a file handle, and the file size will be the same. And it'll work. And you can actually reproduce, run the entire shellcode like this, and you'll see a Trojan execute and stuff without Office at all. Detection mechanisms. Okay, this is mostly for the AV and IDS people. You need to be able to, to reduce false positives, you need to be able to figure out if a file is LASS or not. And you can do that by just looking at the first 8 bytes, DOCF 11E0. And if you have those, the first 8 bytes, so it's very likely that it's an LASS file. And then what you have to do is you have to receive the entire content of this file, and then you use you have to enumerate through all the streams and storages and figure out what type of files you have. You have a Word document, Excel document, or a PowerPoint document. And then you read the contents, and then you parse it as I showed you earlier. And then if you have time, you have to figure out what records are affected. And so basically, if you do generic detection, you get a lot of false positive, right? In order to get good, like very accurate detection, you need to figure out what BIF records or what PowerPoint container / atoms are affected so that you can detect the bad values. So to be more accurate and not have false FPs. We released the Office file format. So it's online, you can go download it. It's available in PDF and another format, and XPS. And given all the information I gave here, and those pictures that I drew, and the documents that we have online, you can actually write your own Excel and PowerPoint parser very easily. And if you write a good one, let me know. And since sometimes it's very difficult for people to, like for example, people will do a bin diff on Office fixes, but most of the time they won't know what records are affected. They just know, oh yeah, that's an integer overflow here, but they won't know exactly how to make a file that will repro that issue. We'll give more information about this at Black Hat Vegas. And this is the team that I work in SWI. So all the bugs that are reported to Microsoft gets assigned to one of us, and we triage it, and we make sure that the fixes are okay. And we have a blog which we talk about vulnerability details. Sometimes we tell you exactly what the vuln is. And it's actually written by people who worked on these bugs, so it's very, I guess you can consider it authoritative. If you want more information, or like if you want to see more information about the vulns, send us an email. If you have a bug to report, send to secure@microsoft.com. And my email, if you have like malicious Office document or whatever you want to share, send it to me, bda@microsoft.com. And that is it. ILFAC must get quite a few of these. The people send him IDB files and stuff, so pray that there's no bugs in IDA. Uh, yeah. Any questions? Oh, yeah. Mm-hmm. Yeah, you can run it in virtual PC. I'm just, I'm just kidding. No, there are like lightweight sandboxes. I mean, they're not made by us, so I mean, I don't particularly endorse them. Oh, not currently, no, but maybe sometimes soon. There's like an app called Sandboxy. I don't know if anybody's heard of it, but it's pretty effective. You open up this, basically it's a lightweight VM. You open it up, all the files are created or like registry keys are changed. It just logs them, and then it tells you that it never commits them to disk, but it just tells you that, oh, hey, you open up Office and there's like rootkit.exe running. So, and you can stop and say that, oh, that's a bad Office document, and not open it again. Is that it? All right, thanks for your time.